Hello guys, this is CodeNCode and this is video editorial for the problem distance in tree. We'll be applying DP. This is a problem related to tree in the graph theory, and we will be applying DP, that is dynamic programming, on this problem to solve it. And of course, this lecture is powered by Unacademy. More about them later in this lecture. So the problem statement is you are given a tree with n nodes, and also you are given an integer k, and you have to find how many pairs are there so that the difference between them is equals to k, right? So k can be as low as 500 and number of nodes are like 50,000. So if I explain this by an example, if this was the input tree and k is equals to 2, so there will be 4 pairs such that the distance between them is 2. 1 3, you can see the distance is 2. Distance, by the way, is measured in this example. The distance is measured using the edges. So the number of edges from 1 to 3 are 2, and number of edges from 1 to 5, basically the distance between these two is 2 again. Similarly for 2 4 and 3 5. So for k is equals to 2, for this given test case, answer is going to be 4. So thought process, how will be starting to solve this problem, how will be approaching this problem to solve. So first of all, think about the worst case, I mean the brute force approach. So we already know that if there are n nodes in a tree, if there are n nodes, there are n square, that is n into n plus 1 divided by 2 number of pairs, right? And so there'll be n into n plus 1 divided by 2 number of paths. So if you apply brute force approach, and for each pair you check the distance between them using the binary lifting, since the distance you can find out in log n time using binary lifting, so the overall complexity would be n square log n, which is of course which will result in TLE for the given test case, I mean for the given problem, because n is equals to 50,000. So it is going to be resulting in TLE if we approach naive, if we use naive approach. So what is the better approach? So how to approach this problem? First thing first, root the tree. It is very important process. When you root the tree and think about the solution, it becomes a bit easy. Think in terms of the subtree. So first of all, we are going to root the tree. It is not necessary to root the tree at node 1, but I'm going to use node 1 as root. You can choose any node as you like. Let me take a moment and explain you why you should go for Unacademy subscription. For competitive programming, of course, when you're going for Unacademy subscription, you are not just paying for 1 or 2 batches, but in fact all of the batches, even for those who have been into the past. So you are getting access to all of the batches. You can learn from your favorite teacher and be part of every single batch or course taken by them. You can interact to them through live sessions, and there are also doubt clearing sessions and a dedicated Discord server where teaching assistants solve your doubts. There are every kind of courses running and batches running for every level of programmer, be it beginners, intermediate or advanced level programmer. Now there is this interview preparation batch, the elite batch. This batch has already started on 24 Feb, and especially for intermediate level programmer, and this batch will help you get ready for upcoming placements. The batch is taken by Deepak Gaur and Riya Bansal. You can see how great educators they are. Riya Bansal herself have been SDE at InterviewBeat and currently SDE at Flipkart, and Deepak Gaur, ACM ICPC World Finalist 2020. So these are educators who will be taking those that elite batch, and you can go for 1, 3, 6 or 12 month subscription. You can apply my code CodeNCode_UA and get 10% off. So let's get back to our lecture. So let's take an example and see some of the observations from there. For example, suppose this is the input tree and k is equals to 2. If k is equals to 2, answer is going to be 10. For example, these are the 10 pairs such that the difference between them is equals to 2, right? 1 4 1 9 2 7, so like 2 7 1 4 1 9 and so on. So these are the 10 pairs. Just pause the video and see for yourself that these the distance between all of these 10 pairs is equals to 2, right? Now there's one important thing here. You see on the left hand side I've written ancestor. What I mean by that is lowest common ancestor. So if you see and observe the pairs, you will see that for all of these pairs LCA is 1. For this pair LCA is 3. Similarly The left hand side represents the LCA and the right hand side are the pair. So for example 5, 8 and 5, 10, the path that goes from 5 to 8, or the path between 5, 8 and 5, 10 has LCA 5, right? So if you know about LCA, LCA is lowest common ancestor. I'm assuming that you already know about that. So LCA, uh, for any pair of node in the graph, there is an LCA, right? You already know about that. And the LCA is actually unique for a given pair, right? I'm talking about tree. So if we count for each node how many for how many pairs it will be their LCA, for each node I count for how many pairs, for how many valid pairs I'm talking about, because even though 2 will be a valid LCA for like pair 29, but it has no valid pair, right? So for each node, if I count how many valid pairs are there such that this node is their LCA, then we can count the total number of pairs. Basically, if I go, okay, how many pairs, how many valid pairs are there? Well, by valid pair I mean the distance between them is equals to k. So how many valid pairs are there such that their LCA is 1, right? So there are 5 pairs. Okay, for 5 I have counted, for 1 I have counted 5, for 2 0, for 3 1, for 4 1, for 5 2, for 6 2, and for 7 8 9 and 10 0, right? So the overall answer would be the sum of all of these, which is 10. How we are going to do that, that is a different thing, but I'm just telling you, for each node we will be counting how many valid pairs are there such that this node is their LCA, right? This is what we are gonna do. This way we'll be counting total number of pairs. How, I mean, what is the implementation, how we'll be implementing that, that is a different thing I'll be telling you in a moment, but that is the whole idea. So for each node we count how many pairs have we as their LCA, that is lowest common ancestor, in their k length path, right? For this test case, of course, the answer is 10 when k is equals to 2. Now if you see, you would find there are two types of path, one that crosses the subtree and one that does not cross the subtree. For example, if you see, the path 1 4 and 1 9 does not cross the subtree. Basically, for 1 4 and 1 9, one of these two will be the LCA. As you can see, 1 for 1 4 1 is LCA, for 1 9 1 is LCA. But for those who do cross subtree, none of the, if I say xy is a pair, neither x nor y will be their LCA. For example, 2 7, neither 2 nor 7 is the LCA, right? For the part 2 7, so you see, these actually cross the subtree. So if you see 2 7, 2 is here and it goes to the LCA and then crosses the part 2 7, right? It has to go to the LCA and then from LCA it has to take a different path. So for LCA, both of these two nodes lie in the different subtree. That's why I'm saying that these kind of path cross subtree. So the counting, for counting the number of pairs, valid pairs, such that they do not cross the path, I mean they do not cross the subtree, is very easy. For this node, how many valid pairs are there such that one is their LCA and they do not cross the subtree? It's simply just it is count of number of nodes which are at distance 2 from this node, right? So how many nodes are there at distance 2 from node 1? Like there are 2 4 and 9. So here you see 1 4 and 1 9. So it is easy to count the pairs which do not cross the subtree. For those who do cross the subtree, there is a little tricky implementation. In fact, we don't have to write two different implementation for counting two different types of pairs, but a single implementation will do the work. I'm just telling you this kind of observation so that it is possible that in next problem that you solve yourself, you might find this kind of observation helpful. So how will be solving this problem? See, so what we'll be doing, of course, for each node we'll be counting in how many pairs are there such that they have this node at their LCA and they are valid pairs. So we'll be solving this using tree DP, and we are going to use DFS. How we do that? Let's see. So as we already know, we are going to apply DP on this tree. So what is this? This is DP array. For each node, we are going to count how many nodes are there at distance, say x, in this subtree. For example, for node 1, how many nodes are there at distance 1 from node 1, right? So there are 3 nodes, 3, 6 and 2. So DP of 1 would be 3. Basically DP of 1 indicates for node 1, and that the other one indicates the distance. So DP of 1 indicates for node 1 at distance 1. So count would be 3, because as you can see in the subtree of node 1 there are 3 nodes which are at distance 1. Similarly, a DP of 1 of 0 would indicate number of nodes which are at distance 0 from node 1. Of course this node itself is at distance 0. So DP of 2 of 1 would be 1 only, because there is only one node at distance 1 from 2, right? So let's start. We would start DFS from node 1, because I'm assuming node 1 is the root. If you are assuming some other node as root, you would start DFS from that node. So we made a DFS call to node 1. As soon as we reach this node, we already know this node itself is at distance 0 from itself. That is why at distance 0 you would increment it by 1. Now we would make DFS call to each of the node. For what we would do to calculate this, how many nodes are there at distance x or y for a certain node, first you need to know first you need to know the same for the subtree of yours, right? So for each child subtree of yours, you have to have the answer itself. So if I know for node 3 how many nodes are at distance 0 and at distance 1 and at distance 2, that same knowledge I can use to calculate nodes at distance 0, 1, 2 from this node, right? If I know there is one node at distance 0 and one node at distance 1 from node 3, right? Whatever node is at distance 0 from 3 is at distance 1 from 1, right? So using the knowledge of this subtree, I can actually calculate this row, this DP row for parent node, right? So for each parent node to calculate this row, it needs to have the knowledge of all child subtree, right? And that is why, first of all, when you reach, what you do, let me just show you the code. As soon as you reach certain node, DP of that node 0 is equals to 1, because that node itself is at distance 0. So there is one node at distance 0 from current node and ODE. After that, what I'm doing, for each child node, I'm making a DFS call if it is not equal to parent. That means if it is not visited, I'm making DFS call. Basically, I'm calculating this row. Basically, I'm calculating the distance of each node from this subtree in its subtree, right? So I will make a DFS call, suppose to 3. As soon as you reach 3, of course DP of 30 would be set to 1. Now from node 3, I'd make a DFS call to node 4, because this is the only child it has. So now we are at node 4, so DP of 4, 0 would set to 1. Now there's nothing to explore for node 4. So in 4 cannot be an LCA of any pair, because for 4 to be LCA of any pair, any valid pair, right, k will be minimum to be 1. So it have to have at least one node in its subtree, right? 2 nodes in its subtree, including 4 itself. So since node 4 does not have any child, so it cannot be a valid it cannot be LCA of any valid pair, right? So that is why if you see here, if current node doesn't have any child, we won't go inside this for loop, right? And this is the place where we are contributing into the result. You see here, result plus equal data that we'll be looking at later. So basically, if the current node doesn't have any child, it cannot be valid LCA of any valid pair, right? And that is why you won't get inside this for loop. And all we are doing is this. Let me tell you what it is. So what is happening here, since we have traversed, since node 4 doesn't have any child, what we would do would simply return, right? Because there's nothing to do. But before that, we know that using this array for node 4, using the row of dp row of node 4, dp row of node 3 will be updated, right? Because it will tell, okay, I have one node at distance 0, 4 node at distance 5, I mean at distance 1, and so on. So utilizing that knowledge, node 3 will be updating number of node at certain level, right? And that's why this whole array needs to be shifted towards right by 1. Why is that so? See, all of the node which were at distance 0 will be at distance 1 from node 3, right? And node 3 will utilize the knowledge. So before returning, we need to shift all of the elements towards right by 1. So all of the node which were at distance 1 from 4 are at distance 2 from 3. That is why we are shifting towards right, right? So this is what we are doing here. So running a loop, and we only need k levels. That is why I'm running from k to 0. So dp of node of I is equals to dp of node of I minus 1. Basically, we are shifting towards right. So now we will return, and as soon as you return, this is happening, right? You made a DFS call from node 3. Remember, just a second. From node 3, we made a DFS call to node 4. So basically, if this is node 4, you made child is node 3, you made a DFS call to node 3, and now after returning, we are traversing the DP array of child node. So what we are doing, we are checking, okay, how many nodes are there at distance 0? How for node 3, not for node 4. Now we are at node 3, so we would see how many nodes are there at distance 0, how many newly found, we can say, since we have traversed this subtree. So this subtree contains the newly found node for node 3, right? So how many newly found nodes are there at distance 0 from 3, right? 0 nodes. Okay, so we would simply increment this by 0, which are nothing. So 1 plus 0 would do nothing. Now how many nodes are there at distance 1? So we see there is one node, one newly found node at distance 1 from 3. If this were to be paired with someone else, some other node, to make the path between them of distance 2, one distance is already there. We need more node at distance 1 from 3, which is not from this subtree, right? And where would you find that? From dp of 3 of 1. dp of 3 of 1 stores number of node at distance 1 which are already found. Till now we have only traversed one subtree. That is why this we haven't found any node at distance 1. If we were to traverse another subtree, which we would do here, so you would see through an example that how it works. So basically, if node 4 were to be paired with some other node such that the distance between them would be 2, one distance is already there. We need nodes at distance 1 from this node, right? That way the distance between them would become 2. So what I'm doing, number of node at distance 1, newly found nodes at distance 1 are dp of child of 1. So number of newly found nodes at distance I times, number of new nodes found at distance k minus I, and then number of nodes which are already found at distance I. If we add these two, the path would become of distance k. So what is happening here, dp of node of 1 is actually number of node at distance 1 already found, right? And dp of child, which is node 4, dp of child of 1 tells you the number of node which are newly found at distance 1. So here the cells that are empty actually 0. So dp of 3 of 1 times dp of 4 of 1, that is 0 times 1 is 0. So result will be added by 0. That means there is no node in the subtree of 3 which is at distance 0 with which we can pair node 4. So 0 would be added into the result. That is exactly what we are doing here. And after that, current nodes dp, that is node 3, will be updated with the number of node at distance I of child. So basically this will be added here. Now if you see, for node 3, number of node at distance 0 is 1, number of node at distance 1 is 1, right? So dp of 3 has calculated. Do we have extra child for 3 to be traversed? The answer is no, so we will simply return. But before returning, what we would do, we would again, what is this, we will again shift it towards right, so that node 1 can utilize it. After shifting, we are here. Again we would do the same thing. Since the DFS of 3 has completed its execution, so we would do again, how many nodes are there at distance 0, how many newly nodes are there at distance 0 from 1? So the answer is 0. 0 would be added here. How many newly found nodes are there at distance 1? There is 1. As you can see, 3 is at distance 1 from node 1, because since we have returned here, so now this loop is running inside node 1 DFS, right? So how many nodes are there at distance 1 in the child? dp of 3 of 1, basically dp of child of 1. Here dp of child of 1, we can see 1. So all of the nodes which are at distance 1 can be paired with all of the nodes at distance 1 again. Why? Because we need total distance to be 2, right? So number of nodes already found at distance 1 times number of nodes newly found at distance 1. So dp of 3 of 1 times dp of 1 of 1. So dp of 3 of 1 times 1 of dp of 1 of 1. Here all of the cells which are not present here are actually 0. So 1 times 1 is 0. So result will be incremented by 0, and this would be added here. Similarly for node 2, all of the nodes which are at distance 2 can be paired with distance 0, right? And how many nodes are there already found at distance 0? That is 1, you can see. So 1 times 1 is 1, so 1 would be added here. So see what happened here. So when number of nodes, the newly found nodes at distance 2 can be paired with number of nodes which are at distance 0, which are already found, right? So number of nodes which are at distance 0 and are already found, you can find here dp of node of I, if I is the current distance I'm looking for, right? So dp of child of k minus I can be paired with dp of node of I. So this number of nodes at distance 2 will be paired with number of nodes at distance 0. So 1 times 1 is 1, so result will be added with 1, so result will become 1, right? And this would be added here. I think I have already added that. Yes, I have already added that. So now you can see for node 3 we have traversed, for node 1 we have traversed and completed this area of DFS, right? So if you complete this area, you would see number of node for node 1 at distance 0 is 1, at distance 1 is 1, at distance 2 is 1. So this area is completed. Now do we have extra child for node 1? Yes, the other child is this, so we'd make a DFS call to node 6. As soon as you reach node 6, you would make dp of 6 of 1 or 6 of 0 to be 1. How many child 6 has? Nothing, so we would simply return, but before returning we would shift it towards right. And now since we have returned to 1, now we would utilize this array to add extra to our result, to basically calculate our result. As you can see, 6 can be paired with 3, right? And that is exactly what you are gonna see here. So when I is equals to 0, what we are doing here, we see how many nodes are there, how many newly nodes are there at distance 0 from parent. The answer is 0. So number of nodes, the number of nodes, newly found nodes at distance 0 can be paired with number of nodes at distance 2 which are already found. So 0 times 1 is 0, so 0 would be added in result, so nothing would happen. How many nodes are there at distance 1 which are newly found? Answer is 1. So these can be paired with all of the nodes which are at distance 1 which have already found. So how many nodes are there which are at distance 1 and already found? Of course 1. So 1 times 1 is 1, so 1 would be added into the result. See, because 3 was already found, and that is why dp of 1 was 1, right? And dp, this node can be paired with all of the nodes which are at distance 1 which are already found, and that is why we are running this loop. Number of nodes, so I'm running a loop from 0 to k, which means how many nodes are there at distance I which are already found. They can be paired with the number of newly found node with distance k minus I, because when you add these two distances, you would get a pair which has distance between them as k, and that is exactly what we want, right? And that is what we are doing here. So we have done this for 6, and now this one would be added here. So basically, if you complete this part of tree, you would see number of node at distance 0 from 1 is 1, number of node at distance 1 is 2 for node 1 I'm talking, and number of node at distance 2 from node 1 is only 1, and that is why we are having 1 to 1 for dp of 1. Now, so are there extra child for node 1? Yes, the next is 2, so we'll make a dfs call to node 2. As soon as we reach node 2, what we would do, dp of 2 comma 0 is 1. Now, do we have any child for node 2? Yes, we have. So we would make a dfs call to that child. So dp of 5 of 0 would become 1. Do we have any child to traverse for node 5? No. So we would simply shift it towards right, and we would simply return to node 2. Now that we return to node 2, what we would do, we would utilize node 5's dp array to update the values of dp array of 2. What we would do, again we would see how many newly found node are there at distance 0. Answer is 0. So 0 can be paired number of node at distance 2 of parent, right? So number of node at distance 0 will be paired with number of nodes at distance 2. Number of node at distance 0 will be paired with number of nodes at distance 2. So 0 times 2 is 0, so 0 would be added into 0. Of course, you can't pair 5. Of course, in this subtree, there's no node except 2. I mean, in this subtree, there are no node at distance 0 which are already found. So newly found node at distance 0, sorry, number of node in this subtree, in subtree of 2 at distance 2, there are no node, right? You can see there are no node at distance 2. That is why it is 0. So 0 times 0 is 0, 0 would be added into result, and this 0 would be added into dp of 2 of 1, right? Now, how many nodes newly found at distance 1 are there? This is 1. It can be paired with all of the nodes which are at distance 1 from this node and already found. The answer is dp of 2, which is 0. So 1 times 0 is 0. 0 would be added here, and this 1 would be added here, right? And after that, of course, how many newly found node which are at distance 2? 0. 0 would be these node can be paired with number of node already found which are at distance 0. The answer is 1, because this node itself is at distance 0. So number of newly found node at distance 2 would be paired with this. So 0 times 1 is 0. 0 would be added here. Nothing would happen. Now we would simply return from here. And yeah, so what has happened here? What has happened here is that from here we have returned to 2, and there is nothing for 2 to do. So we would return from 2 to 1. But before that, we would shift all of this array towards right, and from 2 we have returned to node 1. As we return to node 1, we would utilize this array. So how many newly found nodes are there at distance 0 from this? Because of course 2 was child of this, so we are processing for root node 1 and child node 2. So how many newly found node at distance 0? 0. These node can be paired with already found node at distance 2, right? So 0 times 1 is 0. 0 would be added here. How many newly found node at distance 1? 1. 1 times 2 is going to be 2. 2 would be added here, and this would be added here, right? How many newly found node at distance 2? 1. These can be paired with number of node at distance 0 which are already found, right? So 1 times 1 is 1, which is going to 5, and this is added here. So you see how we are able to calculate the result. Result is going to be 5. You can manually count it. What we have done, we have utilized dp. We have used the dp array to calculate number of node at a certain level for child node, right? For each node, right? And using the dp array of child node, we are able to calculate dp array of parent node. And while traversing the child node itself, we are able to count how many node, for example, this would be paired, since for node 1, if we consider node 1 as LCA, and we have to count all of the node of all of the pair, valid pair for which one is their LCA. For that, this can be paired with, since this is from node 1 at distance 1, this can be paired with all of the node which are at distance 1, right? So 2 can be paired with 6 and 3. And that is exactly what we were doing here. We know how many newly found nodes are at distance 1, which was 2 itself, and this can be paired with all of the nodes which have previously been found and are at distance 1. This array contains all of the nodes which have been previously found and are at distance 0, 1 or 2. So I want all of the nodes which were at distance 1. Before this it was 2, so 1 times 1 times 2 would have been 2, and we had added 2 into the result, and this is how I'm calculating the result. And this way you are calculating the result and finally printing the result. I'll be providing the code in the description of this video. If you have any doubt or query, of course you can ask in the comment section, and maybe if I found there are many queries, I can take a doubt clearing session for this specific problem. So this was all for this lecture. Thank you guys for watching, and thank you for your patience, and till the next video drops, keep coding. Thank you.